there's another interesting industry in the world which is quite heavily affected by the climate change or by the sanctions to prevent the climate change, to reduce the effects. It's the energy production industry. And in Germany, especially in the Lithuania region, in southern Brandenburg, they have a large coal mining industry and very large coal power plants. And in 2038, this will end due to legal restrictions. And we would say, okay, it's a nice deal, move to renewable energies, but the people down there think quite differently because the largest employee has to close there. And so the federal government in Germany and as well as the region and the major employers down there think about, okay, how can we continue afterwards? And how can we live or have this region live again or still living? And we took part of this research in that area with the project PlexiDuck, thinking about how we can reuse the coal transport lines and the coal railway lines to enable public transport in that area region. I don't want to talk about so much about the project. I will talk about one of our products or our prototypes in that region, the train dispatcher in the cloud. But especially I want to talk about how we use SUMO in that area to develop such a railway concept, or how we use it for visualization and test automation in that area. So, but a few words about the train dispatcher in the cloud, which is like one of the core ideas to enable this public transport in that area, because currently there's some kind of railway lines and some kind of infrastructure, but for sure this has not the same quality like the high-speed lines between Berlin and Hanover or Berlin and Hamburg and so on, because they're only carrying coal quite a few times a day. So to enable public transport in that region, we have to modify these lines and the tracks and the CCS infrastructure and so on. And to not say, okay, let's go with the large projects like ETCS or something else. We were thinking about what is the minimal change to the existing infrastructure to enable public transport in that area. So we are working with the so-called German Zugleitbetrieb, which is comparable to the track warrant control, the American track warrant control, or direct traffic control are like synonyms out there, or comparable technologies out there. And it's a very lightweight railway operating procedure following a voice-based protocol. So the train conductor on the train is calling the train dispatcher and say, okay, hey, I'm in A and I want to drive to B, is this possible? And the train conductor is looking at their occupancy sheets, like a print paper, and say, yes, track is free, go ahead, and you can drive there. And then there's a voice protocol, you can see it here on the left, first in German, then in English, to ensure that the communication between both sides is error-free, with some kind of handshake and verification that like the train number and the destination and so on are transmitted correctly via the voice interface. And our train dispatcher in the cloud, we're moving the right side to a cloud implementation. So I'm also facing like issues like having less qualified people for this specific task in the region and so on and so on. We're thinking about a digitalized version of this Zugleitbetrieb or this train dispatcher to actually be able to operate this operating procedure there. And we presented this work a few weeks ago in Dublin on Transport Research Arena. But to give you a short introduction about the architecture and how we injected SUMO in there, this is the architecture of this ZLiC, which is the short for the German word of this, for the train dispatcher in the cloud. So if a train conductor on the train calls this ZLiC system, will end on the right-hand side in the audio gateway, and then a chain of speech-to-text and natural language understanding libraries or components are transferring this voice input to a command to the system. And then on the left-hand side, with the occupancy sheet and some kind of interlocking logic, this command will be processed and will be decided if it's, yes, it's possible to drive there, or thanks for the localization message, and will respond via a text-to-speech over the same gateway as well. And this means that the interface to the train conductor on the train stays the same. And this is like if you talk about certification of such a system, it's like a good idea to take something existing, modify it a bit, but say, okay, well, this is like the same as before. We changed this little part, and we only need to recertify this small part in the end. So in background, there are several components containing of Docker containers communicating via DDS network framework, distributed data service, to actually exchange the messages in between. So how do we want to use simulations in this area? We're currently having implemented two major use cases. The one is visualization or demonstration. Such a system has the lack of like visibility, so there's like the digital occupancy sheet where you can see like basic reservations, but there are no train movements in the end. And so where this was the first minor goal, so to say, to extract the messages and port them to SUMO to actually see running trains through the railway network. And the second part, this was like the major thing of this paper, is like how we can realize test automation with SUMO in this kind of project. So to extract the messages and insert own messages or own trains which are operated by SUMO, so driven by SUMO, but using the same interface as before. Therefore, we inserted a simulation component in the architecture. And the simulation component is between the occupancy sheet and the voice processing area to actually test the logic side of the system, and so it's able to catch all the messages between, so the processed commands and the text in between on the way back through the text-to-speech service, and extracting the information for it, moving it to SUMO for the first step, the visualization, and insert their own messages to the simulation and to the system itself to actually enable then test automation. Therefore, to run the simulation, we need a simulation model, which you can see on the left on the slide. And this is the same data source as the digital occupancy sheet or the interlocking logic. Both are parameterized with a network model containing like topologies, planned routes, and so on and so on. And we're taking the same data source for the SUMO simulation. I have a slide and I think 2 slides to show you more details on this specific part. So especially for the integration of SUMO, we followed 3 steps. The first step was to create the simulation model, as I said before, with the same data source. Second step was capturing the commands and applying them to SUMO. And the third step was then actually to be able to run automated trains. So to create the SUMO simulation model, in the first part, we used our Yaramo toolchain. We developed this toolchain a few years ago, and I think 2 years ago we presented the right-hand side on this conference as well as a poster. The Yaramo model is like a small model containing topology and geography about railway networks, and can be fed from different data sources like PlanPro and Open Railway Map, and can be exported to either formats again, like converting Open Railway Map to PlanPro, or SUMO simulations, or as a parameter for the interlocking logic. Maybe a few words on PlanPro. I'm not sure if you're aware of this. Probably not, because it's like a German specific format, but actually Deutsche Bahn, so the major German railway operator, is actually planning their new stations, their new networks in this kind of format. So it's a data format, XML based, containing all details about topology, geography, CCS infrastructure, and so on and so on. So talking about data quality, this input probably has the highest quality that's ever possible, because Deutsche Bahn is actually building their systems with this data source. And we have PlanPro plannings, for example, for the digitaler Knoten Stuttgart, or earlier Stuttgart 21 or 21, but you cannot say this anymore. And we have a few other PlanPro plannings as well. But we can also say, okay, let's select some kind of area in Open Railway Map, and then we get the model out of it, and you can use it for SUMO there. And we're also inserting, or we're also able to move, or able to export this PlanPro model or the Yaramo instance to the SUMO simulation with the process on the right-hand side, using netconvert and SUMO plan XML in the between and adding routes there to create a config file. In the end, it's like the tool chain I presented you 2 years ago on this conference. So having this YARO instance, we have, as I said before, the same data source for the simulation as well for the logic of the system itself. Second step, capturing the commands. We're mainly dividing between 3 different commands: registration of a new train, localization of a train, so I'm currently located in A or B, which also contains the train completeness, and the last thing is our driving requests. So I want to drive from A to B following an itinerary which maybe cover multiple routes through SUMO. So the first part, the registration, is pretty simple, just a preparation for additional train. Actually, there's no real interaction with SUMO, because in the second part, when we're localizing the train, then we got the current position of the train, and then we can create it in SUMO if it's not existing already. Since this is a circuit, we always, if you reach the end of an itinerary, so reaching our station, then we go into localize again, maybe creating a new drive request. So this is like a circuit, and this happens multiple times. So, yes, afterwards, after localization of the train and creating it in SUMO, we can do a driving request and then SUMO is setting it to the first position of the target destination. So each itinerary from station to station contains multiple, or maybe multiple routes, and SUMO is setting the first route to this, is then operating, or is then driving. And if it's reached the end of a route in SUMO, it will automatically set the next one until it reached the end of the itinerary. Yes, and then needs a new localization there. In the basic operations, each of these 3 different kind of requests are done by a manual user, so the train conductor needs to talk to himself. We're going to see this in a video later. In the automated way for test automation, actually the system is talking with itself. It's generating the same requests, the same messages, and it's also doing a voice output of this, but there's no human needed anymore. Yeah. And afterwards, we created these automated trains, which also has a start position, has an end position here from Spremberg to Boxberg, which are 2 locations in this Lithuania region, has some kind of intermediate stops, and then the logic itself will create the required messages, the required localizations, the required drive requests, and so on and so on, and SUMO will operate the drives and will drive the train through the railway network. And if SUMO and if the train in SUMO reaches the end of an route, it will either set the next route if it's not reached the end of the itinerary, or if it's reached the end of the itinerary, it will do the localization message again. Yes. So we did several experiments with this. Maybe I explain you the slide a bit. What you can see here on the left-hand side, you probably recognize this is a SUMO with a train located at Spremberg at the moment. In the middle, you can see the voice interaction between the train dispatcher and the train conductor on the right-hand side via small voice outputs. And on the right-hand side, you can see this digital occupancy sheet at the moment empty because the train is not driving at the moment. So there was no drive request so far. But after having a drive request, you can see that the track is blocked from Spremberg to Schwarze Pumpe. And when you go to minor railway tracks in minor regions, like not on the high-speed regions, so in some smaller regions, you actually have this kind of paper-based occupancy sheets. So let's see how that works. I'm sorry, this is, since the Zugleitbetrieb is a German specification, also the voice input is in German, but I will translate it to you right away. So I was just asking if the train will be accepted to the system, and now it takes some time to actually process the commands, extract all the information out of it, and until the system responds. will take some time.
Zug 102 ja.
So the ZLiC is confirming that it's fine. Now I'm localizing the train in Spremberg and saying, well, it's here. And what you will see in the left-hand side in a few seconds, it's that the train will be placed in SUMO. This takes some time, and if you think about efficiency, sure, this is not efficient. This has two major reasons. First of all, it's repeating that the train is in Spremberg, and I confirm it again, so this is like the handshake I told you before. So talking about efficiency, can I stop it here? Yeah. Talking about efficiency, for sure, this is pretty, it's not so very fast. Two reasons for that. First reason, this was my personal laptop to execute it, and like the models to extract the speech to text and the natural language understanding, it's like taking very long on my computer. And the second thing is, well, that's fine. We do not need to make it, we need to make it a bit faster, sure, but it doesn't need to be right away, because these tracks where you can apply such a system are so less crowded that it's just fine to wait a few seconds. Yeah. Can I jump in the middle of the video here somewhere? Yeah, I'm sorry. So maybe I just add a few more things and mute it for a second, because when the driving request is coming, you can see that the train actually is driving from A to B. A few more words on the intersection of SUMO. So the ZLiC is created by an ontology-based development approach, or model-based development approach, that every component is defined in a specific model, and then the messages between are also defined by this model. And to insert SUMO there, we just added in a few lines of code to say, okay, there's another component, please reroute the messages. And then there's like a flag where you can say, okay, run it with simulation or without simulation. And okay, this was the confirmation. And this is like a minor change to the system itself to switch between simulation mode and productive mode, which is actually pretty nice. So we'll move it to volume again. So there's the train on the left-hand side. And now the driving request is coming in a few seconds and ask if you can drive to Schwarze Pumpe, which is the next station on the route. This is like, can I drive down to Schwarze Pumpe? I will mute it here again to continue a bit of explanations. So our system is communicating with SUMO on the one hand side to place the trains and set like speeds and so on, but there's also a second direction. There was a link from the interlocking logic to the simulation component. There's a second Tracy connection. And this is because the ZLiC system is controlling the light signals in SUMO, and is then able to actually modify like the infrastructure there to drive the trains, or be able to operate like this. So the handshake between the driving requests contains four parts, confirming in both directions to make sure that there's no mistake in destination and train number, to ensure, or this ensures that there's no error in the voice interaction between the ZLiC and the train conductor on the train. So yeah, now the train is driving to the next location, reaching the next location, it will localize it again, and then the same process starts from beginning. Having the automated trains looks like a bit different, because now the system is talking to itself, and which sounds like quite funny, but we actually implemented different voices for both to make it a bit interesting, more interesting.
Wird Zug 203 angenommen?
It's like the same process as before. I think I will skip, due to time reasons, the same full video. If you're interested in it, the publication contains links to these videos. Just open on your computer. And if you're not familiar with German language, I'm very sorry, but you can put the sheet beside this. So talking about next steps in future work, the first thing is we talked about test automation, and therefore we're thinking about creating a test suite to actually be able to run continuous testing processes during the development of the system of ZLiC. The next idea would be to include also the voice interface into the testing environment, so move the simulation component before the voice processing. This has some advantages and disadvantages, like we could test the voice interaction, but maybe the logic component not so clearly and so on. So this is current development, where to put this simulation component. And then multi-line support would be thinkable. It's currently not possible in ZLiC. This is a minor thing and not really related to SUMO, but we could also think about different use cases for SUMO, like use it for predictions on arrival times and so on, to do like communicating with the passengers and so on. So to sum it up, we created the ZLiC, the system on the left-hand side, to be able to have in railway operating procedures in these minor developed areas to enable public transport there on the existing train connections or existing tracks with minimal effort in changing operating procedure. And afterwards, we used SUMO to visualize it on the one hand side and use it for test automation on the other hand side. And yeah, that concludes my talk.